Assalamualaikum, this is Zainab Ijaz and today the topic of our discussion is Laplace Transform. The contents that I am covering in this video is an abstract introduction, definitions of Laplace transforms, properties, its plotting on MATLAB and software Mathematica. And I am also giving you some example. The concepts of Laplace transforms plays a vital role in a wide field of science and technology, such as electric and communication, quantum physics, solutions of ODEs and partial differential equations, and these explanations will provide students with a solid foundation in the fundamental of Laplace transform and gain an understanding of some very important and basic applications of this transformation. This transformation is named after the mathematician and renowned astronomer Pierre-Simon Laplace, who lived in France. And this Laplace transform is used to convert many functions such as band sinusoidal function, exponential function, sinusoidal functions into algebraic function of a complex variable f. Because in mathematics, transformation deals with the conversion of one function to another function that may be not in the same domain. So let f of t is a function of t, and this function is defined for all values of t which is greater than or equals to 0. Then the Laplace transform of this function is generated by f of s, and it is represented by a formula that is 0 to infinity integral e power minus s t f of t dt. And by using Laplace transform, I am able to convert a function which is in t space into a function in s space. There are many properties of Laplace transform. Some of them is as follows. The first property of Laplace transform is linearity property, and in this property we can find Laplace transforms of individual function, and the property is mentioned over here, where in this property a and b are any constant while f1 of t and f2 of t are functions. The second property is shifting property, and in this property, if I say that if a Laplace transform of f of t is capital F of s, then Laplace transform of exponential power LTF of t is capital F s minus a. The property is mentioned over here. So if I have a differential equations and I am supposed to find the Laplace transform of this differential equation, then there the following procedures I mentioned over here, which you have to follow in order to find the Laplace transform of any differential equation. So if there is a differential equation which is mentioned over here, you just have to apply Laplace transform, then you have to solve it, and you will get your answer in S domain. And if you want to get your answer in t domain, then you will find your answer in t domain by taking an inverse Laplace transform of your answer. So some of the Laplace transforms of basic functions are like if you have a function of 1, then its Laplace transform is 1 over s. If you have a function of t, its Laplace transform is 1 by s square. If you have a function of sine kt, its Laplace transform will be k over s square plus k square. And you have a function of exponential at, then its Laplace transform is 1 over s minus a. There are many advantages of Laplace transform. Some of them is mentioned over here. It is used in electrical circuits. A Laplace transform is used for the analysis of linear time invariant system, and a Laplace transform is widely used by electronics engineers to quickly solve differential equation occurring in the analysis of electronic circuits. The Laplace transform is usually used to simplify a differential equation into a simple and solvable algebra formula. Even when the algebra becomes a little complex, it's still easier to solve than solving a differential equation. This transform is most commonly used for the control system, and the transforms are used to study and analyze systems such as ventilation, heating, and air conditions, etc. These systems are used in every single modern day constructions and buildings. Laplace transforms are also important for process controls. It aids in the variable analysis, which, when altered, produce the required result. An example of this can be found in experiments to do with heat. The control equation for a dynamical control system, whether electrical, mechanical, thermal, hydroelectric, etc., can be represented by a differential equation. The system differential equation is derived according to a physical law governing the system. In order to facilitate the solution of a differential equation describing a control system, the equation is transformed into an algebraic formula. And this transformation is done with the help of Laplace transform technique. That is, the time domain differential equation is converted into a frequency domain algebraic equation. But Laplace transforms also has some limitations. Laplace transform can only be used to solve complex differential equation, and like all great methods, it does have disadvantages, which may not seem so big. That is, you can only use this method to solve differential equation with known constants. If you do have an equation without the known constant, then this method is useless, and you will have to find another method. So in conclusions, we say that the Laplace transform is a powerful tool which using in different areas of mathematics, physics and engineering. With ease of applications of Laplace transforms in many applications, many research software have made it possible to simulate the Laplace transformable equation directly, which has made a good advancement in the research field. So now let's find the Laplace transforms of functions by using MATLAB. If I have to function f of t and I have to find the function in a frequency domain, then what will we do? I do just I apply Laplace transform on a function f of t. This will give me an answer in frequency domain. In order to find Laplace transform by using MATLAB, you need to specify the variable t and s or and on MATLAB, and these variable t and s are symbolic ones. This is done with the command that is mentioned over here. Next, you find the function f of t, and the actual command to calculate the transform is f is equals to Laplace fts. And in order to make the expressions more readable, one can use the command simplify and pretty. Now let me give you an example. For example, I have a function which is mentioned over here, and I have to find the Laplace transform by using MATLAB. Then just you have to follow the procedures that I mentioned in previous slides, and you will get your answer. And in order to simplify your answer more, then you just have order a command that is pretty answer. Then you will get your answer. And let's take an example of an inverse Laplace transform. And the command one uses now is I Laplace. One also needs to define the symbol t and s. Now let's calculate the inverse of the previous function f of s. So main procedure what you just have to follow is same as I mentioned in previous slides, and you will get your answer by just following that steps. We can also solve Laplace transforms ODEs by Laplace transforms on MATLAB because MATLAB has some powerful features for solving differential equations of all types. We will explore some of these features using Laplace transforms, and the approach here will be that of a symbolic math toolbox, and the result will be the form of functions, and it may be really plotted with MATLAB. So this is an equation which is mentioned over here, and this is a ordinary differential equation, and I have to solve these equations on MATLAB. Then I type a command sims stry because these are our variables and symbols. Then I write a function, and I have find its Laplace transform, and then I have written here y1 expression, y2 expressions, and solution commands, and then I have written here pt in order to make our answer more simplified. And in order to make our title more simplified, then you have to just mention all steps on MATLAB, and then you will get your answer easily. These are our required answers of the differential equation that I mentioned in previous slide, and I also plotted here. Next, one more example is written over here, and you just have to follow all the steps that I mentioned in previous slides, and you will get your answer easily. Now let's find the Laplace transform of some signals, that is unit impulse signals, unit step signals, exponential signals, parabolic signals, and cosine signals, and ramp signals. In order to find the plots of unit impulse signal, the all coordinates are mentioned over here, and there this is a plot of a unit impulse signal. In order to find a plotting of a unit step signal, then this is a plot of a unit step signal, and all its mathematics coding on MATLAB is written over here. And the next RAM signal, its MATLAB code is also written over here, and I am also showing you the plot of RAM signal. And these are some plots that can be found by using MATLAB. Now, by using MATLAB, we can also find a 3D graph of Laplace transform of a function. This is a function, and now I have to find its 3D graph. Then what you will do, you just have to type these commands that I mentioned over here, and these commands will give you the plot that is beside these commands. Now, in order to write its combined commands, then I have just find impulse signal, unit step signals, RAM signals, and in order to make its plot combined, then these are some commands that you have to type on MATLAB, and this on then MATLAB will give you this graph. Now let's take an example. For example, I have to find the Laplace transform of a function, and these are ordinary differential equation, and with the initial conditions, and we have to take its Laplace transform. Then you just have to follow all the procedure that I explained to you earlier, and after solving handwritten solving, you will get y of s, and in order to solve the same differential equations on MATLAB, you will get the same answer as you find by using hand. Its plot is also written over, mentioned over here. And MATLAB has wide applications in physics like damped harmonic applications, and its applications. It's has a differential equation same like I explained earlier with some initial conditions, and its MATLAB code is also mentioned over here. You can easily calculate it. We can also do some circuit analysis by using MATLAB. For example, this is a circuit and we have to find the voltage across the inductor in series RL circuit. Then these are the commands that you have to type on MATLAB. This will give you a plot between amplitude V and between time, and these are plots showing you that that circuit is that circuit in which we have to find voltage, and this will give you graph like this. There is another circuit, RLC circuit, and from this circuit we have a capacitor attached inductor with a voltage and resistor, and in order to find the total amount of charge, we just have to solve as the we just have to solve it. I have it's written all these basic steps that you have to adopt, and in order to solve it on MATLAB, you can easily solve it on MATLAB by typing these commands. And by typing these commands, you can easily calculate Q of S, and your answer is the same as you get by using hands. Now let's do all these things on Mathematica. As I explained to you earlier, all these steps you have followed, you have adopted it, and you have learned. You just have to do all those commands. You just have to write all those commands on MATLAB. Now I explained to you how you can use Mathematica. How can you find Laplace transforms by using Mathematica? As Mathematica is used to take a complicated problems like Laplace transforms, and it reduced to a series of commands. The output from each command is used as the input from the next, and the advantage to this approach is that you focus on what operation you perform to solve your problems rather than how you perform each operations. After explaining each command and what it does, they will all be put together at the end of document to illustrate how an entire problem can be worked out using Mathematica. As Laplace transforms are fairly simple and straightforward, as we can easily be serious, we can say that Laplace transforms are fairly simple and straightforward by using Mathematica rather than on MATLAB. If on MATLAB it is a little bit difficult than Mathematica. You can I'll find Laplace transform by using both softwares, but I like to find Laplace transforms by using MATLAB. So Laplace transforms are fairly simple and straightforward. And in order to find the Laplace transforms of t square plus cos t, you just have to write these commands on Mathematica, and you will get your answer easily. There are two ways to generate a unit step function. You may use either the unit step command or Heaviside theta command. Both commands are mathematical functions like sine or cos, and therefore you can multiply it with another expressions in order to take the Laplace transforms of a t-shifted functions. And in order to take Laplace transforms of unit step signals, and these are the commands that I have mentioned here. We can also find Laplace transforms of impulse functions, which is a structure very much the same as the unit steps functions. All that changes is the name of the command. You use the Dirac delta command with the same syntax. And in order to find Laplace transforms of Dirac delta command, and these are the commands that I mentioned over here. These Laplace transforms convert Dirac delta command, which is in t domain, into a frequency domain. You can also solve initial value problems. You can also solve differential equations by using Mathematica. To put everything together, I define a shortcut for the differential equation I wish to solve. I pick a one that uses an impulse function, and these are the commands that you have to type on Mathematica, and you will get your answer easily. You can also find Laplace transforms of derivatives. You can also find Laplace transforms of integrals by using Mathematica and MATLAB. And this is all from my side. Hope you all understood Laplace transforms, how to Laplace transforms on Mathematica, how to Laplace transforms on how to find Laplace transforms on MATLAB. Thank you very much.